Welcome to lecture 28 of Plant Design and Economics. We will continue our discussion on hierarchical approach to process synthesis. In the previous lecture, we have talked about various levels of decisions and discussed the level 1 decision, which was about batch versus continuous operations. Today, we will talk about level 2 decisions. So, hierarchical approach to process synthesis design at level 2. So, level 2 decisions. We have talked about that there are 5 different levels: batch versus continuous, input output structure of the flow sheet, recycle structure of the flow sheet and reactor considerations, general structure of the separation system, and then under that vapor recovery system comes first, and then comes liquid recovery system, and at level 5 heat exchanger network. Now, we have talked about batch versus continuous processes, that is decisions at level 1. Since batch processes are time dependent, they have a different structure and very different alternatives from continuous plants. So, the hierarchical approach to process synthesis, as we discuss here, is essentially restricted to continuous processes. So, today we will look at level 2 decisions, which is about input output structure of the flow sheet. So, before we go into the details of decisions at level 2, we quickly review the hydrodealkylation process of the toluene that we discussed in the previous class. So, you know that toluene reacts with hydrogen to produce benzene and methane, and then 2 molecules of benzene undergoes reversible reaction to produce 1 molecule of diphenyl and 1 molecule of hydrogen. Now, the flow sheet that we developed was hydrogen and methane are heated up, also toluene is heated up to vaporize and to raise temperature. They are mixed, fed to the reactor, where this hydrodealkylation reaction takes place. So, the effluent stream from the reactor will contain desired product benzene, undesired byproduct diphenyl, and also hydrogen, methane and unreacted toluene. This reactor effluent stream will be cooled and then flashed. The vapor product will mostly contain hydrogen and methane. We would like to recycle the hydrogen, but purge out the methane. So, mostly the hydrogen stream is compressed, heated and fed back to the reactor again. The liquid stream that comes from the flash will mostly contain benzene, toluene and diphenyl, but we will also have some amount of dissolved hydrogen and methane. So, when this stream goes to the stabilizer column, hydrogen and methane are separated out as top product. The bottom product, which contains benzene plus toluene plus diphenyl, goes as feed to the second column, which is known as benzene column, and benzene comes out as a top product there. The bottom product is mostly toluene and diphenyl, which are separated as toluene and diphenyl in the third distillation column. The toluene, which comes as top product, is heated and fed back to the reactor as recycle, and the unwanted diphenyl comes as bottom product. Now, let us discuss the decision at level 2 in more detail, and this decision is all about input output structure of the flow sheet. Input output structure defines the overall material balance boundary of the flow sheet. The recycles affect only internal process streams, but not the overall input output material balance. So, we draw a box around the entire process and focus attention on input of raw materials and output of products as well as output of byproducts. The rule of thumb that one uses here is that we need to try to recover more than 99% of all valuable materials. Then almost every flow sheet has one of the following two structures that we just discussed now. The first flow sheet, the feed streams enter and the products and byproduct stream comes out. Look, there is no recycle, there is no purge. So, no reactant leaves the process. The reactants are all converted to products and byproducts. Now, look at the second flow sheet. Here you see the existence of a purge stream and recycle loop. So, this kind of flow sheet you will often see in gaseous reactions. If the gaseous feed stream contains an impurity or inert, or an impurity is produced during the reaction, this impurity or the inert must be purged out, otherwise it will build in the recycle loop. Note that the unconverted reactant you would like to send back to the reactor as recycle, but the inert or the impurity must be purged out from the process, otherwise it will build up in the recycle loop and stop the process. So, in such a process flow sheet, you see that there is a purge stream. So, there is loss of some reactants through this purge of gaseous streams. So, in general almost every flow sheet will have either this structure or this structure. For inexpensive and of course non-toxic raw materials, it may be cheaper to lose them in an exit stream rather than to recover and recycle them. If the raw material is toxic, then for environmental regulations, we will not be allowed to exit it to the atmosphere. But if the raw material is non-toxic and not expensive, then it may be cheaper to lose them in an exit stream rather than to recover and recycle them, because to recover and recycle these inexpensive raw materials, you have to invest money. So, for inexpensive raw materials, it may be cheaper to lose them in an exit stream. We have discussed about synthesis ammonia long back. We have seen that purge was necessary to avoid the accumulation of inert gases. However, if you use a membrane based separation process and if the membrane technique is competitive and affordable, the reactants nitrogen and hydrogen can be completely recovered or almost completely recovered from the purge, and this will reduce the overall material consumption. Note that when you use gas recycle and purge stream, it adds a design degree of freedom. So, the reactant composition of the purge stream or the excess reactant fed to the process will become a new design variable in the presence of gas recycle or purge stream. This we will discuss in more detail later. So, the reactant composition. So, in case of say the HDA process, the composition of hydrogen in this purge stream or the excess amount of hydrogen that is fed to the process will be considered as a new design variable. So, the presence of gas recycle and purge stream adds a design degree of freedom. Now, the decision that we must make to fix input output structure of process flow sheet are as follows. First, should we purify the feed streams before they enter the process? So, we are now going to raise several questions, and these are the decisions that we must take to fix input output structure of the flow sheet. These are level 2 decisions. First, should we purify the feed streams before they enter the process? Should we remove or recycle a reversible byproduct? Should we use a gas recycle and purge stream? Should we recover and recycle some reactants? How many product streams will there be? What are the design variables for the input output structure, and what economic trade-offs are associated with these variables? So, we need to take decisions about all these issues that we just discussed. Now, we will go one by one and see what are the heuristics or design guidelines available for these questions. First, what is the design guideline or heuristics available for feed purification? So, this will answer to the question, should we purify the feed before it enters the process? If a feed impurity is not inert and is present in significant quantities, remove it. Otherwise, it will lead to loss of raw materials and more complicated separation system will be required to recover additional byproducts. If a feed impurity is present in large amount, remove it. If a feed impurity is catalyst poison, obviously remove it. Otherwise, it will hamper the reactor operation. If a feed impurity is present in a gas feed, as a first case, process the impurity. If a feed impurity is present as an azeotrope with a reactant, often it is better to process the impurity. If a feed impurity is inert, but it is easier to separate from the product than the feed, it is better to process the impurity. If a feed impurity in a liquid feed stream is also a byproduct or a product component, usually it is better to feed the process through the separation system. So, these heuristics or design guidelines are available, which will help us decide whether we should separate the impurity from the feed, that means remove it, or we can actually process the impurity with the feed. Process alternatives. If you are not certain that our decisions are correct, we consider the opposite decision as process alternative. Feed purification involves cost. So, always keep the process economics in mind. Next, we will ask whether to recover or recycle reversible byproducts. So, what heuristics or design guidelines are available to decide whether to recover or recycle reversible byproducts or not? Now, benzene to diphenyl reaction is reversible. So, you can recycle the diphenyl back to the reactor and let it build up in the recycle loop until it finally reaches an equilibrium. When it reaches an equilibrium, the forward reaction by which diphenyl is formed from the benzene will be equal to the backward reaction by which benzene is formed from diphenyl. Note that selectivity will not be affected here. Now, if we recycle byproducts in reversible reactions, it will lead to oversizing of all equipment in that recycle loop, because you now have to accommodate the increased equilibrium flow. But if we decide to remove the byproduct from the process, then we pay an economic penalty because of increased raw material cost that was converted to reversible byproduct diphenyl. So, basically the cost of toluene and the cost of fuel value of diphenyl you look at. So, the toluene cost minus the fuel value of diphenyl, this much of economic penalty will be there if we decide to remove the byproduct from the process. So, since the benzene to diphenyl reaction is reversible, we can recycle the diphenyl to the reactor and let it build up to the recycle loop until it reaches an equilibrium. But if we do that, it leads to oversizing of the equipment in the recycle loop, and if we decide to remove, we pay an economic penalty. So, the decision involves economic trade-off. So, there is actually no easy heuristics or design guides available for this decision, because decision involves economic trade-off. So, you have to do an economic analysis to come up to a proper conclusion. Next, whether to use gas recycle or purge stream. So, what design guidelines or heuristics are available? Look at the flow sheet. You have the purge stream as well as the recycle stream. So, that to use such gas recycle and purge stream in a gaseous reaction. So, now let us talk about the heuristics or design guidelines that are available. In a gas phase reaction, whenever we have a light component, what is light component? A light reactant, a light feed impurity or a light byproduct that has a boiling temperature lower than the boiling temperature of propylene, which is minus 48 degrees Celsius. So, in a gas phase reaction, whenever we have a light component that boil lower than propylene, use gas recycle and one or several purge streams. Lower boiling components normally cannot fully recovered by condensing at high pressure with the available cooling water. So, lower boiling components normally cannot be fully recovered by condensing the stream at high pressure with the available cooling water. It means that you will require both high pressure as well as refrigeration, and refrigeration is an expensive operation. So, it may be cheaper to lose some amount of reactant by purge. So, this is the justification behind these heuristics. However, always consider membrane system to recover efficiently valuable components from purges. But note that membrane systems may be expensive, so you must perform economic analysis. So, for inexpensive components, may not be economically viable to be recovered from the part stream using membrane separation system. But you always consider that as an alternative to recover efficiently valuable components from purchase. Next, do not recover and recycle some reactants. What kind of reactants? Which are inexpensive, such as air. Air is used in several industrial operations. For example, in hydrocarbon oxidation, we use excess air for complete combustion of fuel. Now, because of low cost, the air is not normally recycled. The exit point of gases is the flare. Oxygen has replaced air in many processes. There is an advantage in replacing air by oxygen. There will be significant reduction in the volume of emission. Also, the reaction rate will be improved, as well as selectivity can also be greatly improved. So, that is the reason that oxygen has now replaced air in many industrial operations, so that you can significantly reduce the volume of emission as well as improve reaction rate and selectivity. Now, how do you compute the number of product streams leaving the process? Let us follow the steps as we discussed now. First, examine carefully the reactor outlet and list all the components. So, focus your attention on the reactor outlets and list all the components. This list includes all the components in the feed streams and all the reactants and products that appear in every reaction. Assign a destination code to each component. Arrange the components by their normal boiling points and group neighboring components with the same destination. We will see what are those destination codes in the next slide. So, these are the steps that we follow. First, we examine carefully the reactor outlets and list all the components. Assign a destination code to each component. Arrange the components by their normal boiling points and group neighboring components with the same destination. The number of all groups minus the recycled streams gives the number of outlet streams or number of product streams. So, number of product streams or number of outlet streams is equal to the number of groups minus the number of recycled streams. So, this is based on the idea that it is never advantageous to separate and then mix two streams. There is no point. You do not separate two streams and again mix them. However, formation of azeotrophs or solid components may change this rule. Now, these are the destination codes and the associated component classifications. For example, if you have gaseous byproducts and feed impurities, this stream will be associated destination code vent. To reactants, reaction intermediates, we will assign destination code recycle. Gaseous reactants plus inert gases and or gaseous byproducts, we will assign recycle and purge as destination code. Byproducts to fuel, we will assign fuel as destination code. Primary product will be assigned primary product as destination code. So, we have a list of destination code and the associated component classification. You use this list to assign a destination code to each component. Now, let us take this example from the hydrodealkylation process to understand how to compute number of product streams. So, what are the components we have? Hydrogen, methane, benzene, toluene and diphenyl. So, I arrange them according to normal boiling point. Note that both hydrogen and methane boil lower than the propylene. Propylene has boiling point minus 48 degrees Celsius, whereas hydrogen and methane has much lower boiling point. So, thus we will use a gas recycle and purge stream. So, we have seen the heuristics that whenever in a gas phase reaction the light components boil below propylene, we will use gas recycle and purge stream. So, use gas recycle and purge stream. Now, we have arranged the components according to their boiling point and assigned a destination code. Hydrogen and methane has been assigned recycle and purge, benzene has been assigned primary product, toluene has been assigned recycle and the diphenyl has been assigned fuel. So, how many product streams are there? We have 3 product streams: recycle and purge, primary product and the diphenyl or fuel product. At each stage of the development of a flow sheet, you must take care that all products, byproducts, impurities must leave the process. Now, the design variables. For complex reactions, the product distribution can be correlated as a function of certain design variables. These design variables affect overall material balance of the process. What are those design variables? Conversion of limiting reactant. For example, in the HDA process, the limiting reactant is toluene. So, conversion of toluene will be a design variable. Molar ratio of reactant, reactor temperature, reactor pressure, these are all design variables. If the activation energy of all the reactions are same, then this correlation describing product distribution will not depend on temperature. Similarly, if we consider liquid phase reaction, then the product distribution correlation will not be a function of pressure. Also, for gas phase reaction, if there are same number of moles of products and reactants, then also the correlation describing the product distribution will not be a function of pressure. If excess reactants are used due to reactant not recovered or gas recycle and purge, then the excess amount is another design variable. So, along with conversion of limiting reactant, molar ratio of reactant, reactor temperature, reactor pressure, the excess amount of reactor, the excess amount is also another design variable. Now, we will see how to develop material balance for our process. So, let us first discuss the procedure. We start with the specified production rate. From the stoichiometry, find the byproduct flows and the reactant requirements. Calculate the impurity inlet and outlet flows for the feed streams where the reactants are completely recovered or recycled. Next, calculate the outlet flows of reactants in terms of a specific amount of excess for streams where reactants are not recovered and recycled. Calculate the inlet and outlet flows for the impurities entering with the reactant streams in the previous step 4. So, this is the procedure. Now, let us take the example of HDA process and develop the material balance. Before that, let us discuss about the limitation of this approach. What we assume that we are able to completely recover all valuable materials. The heuristics we use that we should be able to recover 99% or more of the valuable materials. Here we are assuming the 100% recovery, complete recovery, which may not be possible always. No rules of thumb available to fix the design variables. It is important to find the neighborhood of the optimum values of the design variables. When your process has several products, the material balance for such multi-product plant becomes much more difficult. Now, before we discuss the material balance in details, let us define two terms, selectivity and conversion, which we will be using. Conversion is reactant consumed in the reactor divided by reactant fed to the reactor, and selectivity is desired product produced divided by reactant fed to the reactor multiplied by stoichiometric factor. Stoichiometric factor is the moles of reactant required per mole of product. So, now let us develop the material balance. First, look at selectivity and reaction stoichiometry. We are taking the hydrodealkylation of toluene as example. So, look at the flow sheet. The flows are indicated and these are all in terms of moles per hour. Selectivity is the fraction of toluene converted in the reactor that corresponds to the benzene flow at reactor outlet. So, according to this selectivity definition, it will be the amount of benzene divided by toluene. Fe is the excess hydrogen fed and YPH is the purge composition of the reactant. Pb is the desired benzene production moles per hour. We assume all benzene is being recovered. FFT is the fresh pure toluene fed to the process, again moles per hour. We assume that all the toluene is getting converted, and PrCH4 is the amount of methane produced in the process in moles per hour. Note that in the HDA process, methane is produced as well as enters the process as impurity. Using stoichiometry and material balance, we can find all input and output flows in terms of design variables, selectivity and either excess hydrogen Fe or the hydrogen concentration or the mole fraction of hydrogen in the purge stream, which is YPH. So, let us see how you do that. Now, look at the reaction. So, 1 mole of toluene reacts with 1 mole of hydrogen to produce 1 mole of benzene and 1 mole of methamine. So, from stoichiometry we can say that FFT will be equal to Pb by S. Note that the selectivity is equal to benzene by toluene. So, the benzene is Pb moles per hour. So, FFT will be Pb by S moles per hour. Also, in the process, the amount of methane produced is same as the amount of benzene. So, 1 mole of benzene and 1 mole of methane is produced. So, the amount of methane produced is also Pb by S moles per hour. If S is the fraction of toluene converted to benzene, then 1 minus S must be lost to diphenyl. Let the amount of diphenyl produced is Pd. So, Pd moles per hour. So, from stoichiometry we can say that P d will be equal to f f t into 1 minus S by 2. Why 1 minus S by 2? Because 2 moles of benzene gives 1 mole of diphenyl. So, P d equal to f f t into 1 minus S by 2, and we already seen that f f t equal to P b by S. So, I get P b by S into 1 minus S by 2. So, feed toluene has no impurity. We can find the diphenyl fluoride P d and the toluene flow that goes to the process f f t in terms of selectivity and given benzene production rate. Now, let us look at the recycle and purge stream of the HDA process. We will first do hydrogen balance. If we feed excess amount of hydrogen to the process, this hydrogen has to leave with the purge stream. The flow rate of the purge stream is P g and the mole fraction of hydrogen in the feed is Y f h and mole fraction of hydrogen in the purge stream is Y p h. F g is the makeup gas stream flow rate. So, this is now total amount of hydrogen fed to the process will be F g times Y f h. So, this has to be equal to the net hydrogen consumed plus hydrogen lost in the purge. Now, the net hydrogen consumed will have two parts. One is hydrogen is fed to the process, is a reactant, as well as hydrogen is produced during the process. So, we can write Y f h into F g, which is the total amount of hydrogen fed to the process, is equal to the net consumed P b by S, this is required in the process, minus this is produced the same amount of diphenyl. See, the amount of diphenyl produced and the amount of hydrogen produced is same, and we have seen in the previous slide that amount of diphenyl produced is P b by S into 1 minus S by 2, and F e is the excess hydrogen fed. So, excess hydrogen fed has to leave with the purge. So, it has to be equal to Y p h into P g. So, this is the hydrogen balance. Similarly, you can also write the methane balance. Let P c H 4 equal to purge rate of the methane. So, this is the flow of methane leaving the process with the purge stream. So, purge rate of methane, which is P c H 4, will be equal to methane in the feed plus methane produced. What is methane in the feed? The mole fraction of a hydrogen in the feed is Y f h. So, Y minus f h must be the mole fraction of methane in the feed multiplied by the F g. So, will be methane in the feed and plus the methane produced in the process, which is same as amount of benzene produced, which is P b by S. Note that this methane flow in the purge will be the mole fraction of the methane in the purge stream multiplied by P g. If Y p h is the mole fraction of hydrogen in the purge stream, Y minus p h will be the mole fraction of methane in the purge stream. So, the total purge flow rate P g will be equal to excess hydrogen F e plus total methane P H 4. So, now we have expression for both. So, Fe, the excess hydrogen, plus the total methane in the purge rate. So, this gives me the methane balance. Now, what should be my choice of design variables? Excess hydrogen Fe or hydrogen mole fraction in the purge YPH. We should select YPH because it represents a mole fraction. So, thereby it is bounded between 0 and 1, lower bound is 0, upper bound is 1. So, Fe, the excess hydrogen will be equal to YPH into Pg. So, YPH equal to Fe by Pg. Now, we can compute this makeup gas rate Fg and the purge rate Pg in terms of the mole fraction of hydrogen in the purge stream, which is the design variable. To do that, you write the hydrogen balance that we have written in the previous slide, also write the methane balance, just add up these two. So, we will get an expression for the purge rate Pg. And now, if you combine the methane balance and the expression for the purge rate, you can solve for Fg, which is the makeup gas rate in terms of selectivity S and hydrogen mole fraction in the purge stream, which are these two are design variables. Note that Pb is the benzene production rate, which is the desired rate. So, that will be given. Also, YFH is the feed concentration of the hydrogen, mole fraction of hydrogen in the feed. So, we are able to express Fg in terms of design variables S and mole fraction of hydrogen in the purge stream. So, for a given design rate, for a given design flow rate for benzene, we can find all input and output flows FFT, PD, Fg, Pg in terms of design variable selectivity and either excess hydrogen Fe or mole fraction of hydrogen in the purge YPH. Now, economic potential. The alternatives generated by the hierarchical approach may be evaluated by means of an economic potential EP. At the nth level of the hierarchical procedure, we can write EPN equal to revenue from selling of products, byproducts minus expenses including cost of raw materials, utility, waste treatment, annualized equipment, operating cost, etc. Note that this economic potential is a function of conversion, selectivity, reaction temperature, pressure, etc. That means design variables. So, basically economic potential is the revenue from selling products and byproducts minus all the expenses of raw materials, utility, waste treatment, annualized equipment cost, annualized operating costs, etc. At level 2, the economic potential EP2 will be product values plus byproduct values minus raw material cost. So, at this stage, if economic potential is less than 0, it means that raw material is more expensive than the product. So, we have to find less expensive raw materials. Also note that if you are using feed compressor, we have to subtract annualized equipment and the operating cost from the expression of EP2. For the hydrodealkylation process, EP2 will be benzene value plus fuel value of diphenyl plus fuel value of purge minus toluene cost minus makeup gas cost. We can plot the economic potential level 2 EP2 as a function of conversion to find the domain of feasible design. So, we have plotted the EP2 versus conversion for various values of excess hydrogen 0.1, 0.4 and 0.7. What we see that EP2 is very sensitive with excess of hydrogen. The maximum conversion is limited at approximately 0.8. However, there is no indication about the lower bound. You see that in this entire zone, it is quite flat. It does not change much, the economic potential does not change much with conversion. So, the lower bound of the conversion is not apparent. no indication of the lower bound here. The lower bound will be set when you evaluate the cost of recycles at level 3. Okay, we briefly discussed that process alternatives can be generated when we take an opposite decision. During development of HDA process, the following decisions were taken: not to purify the hydrogen feed stream, to remove the diphenyl from the process, to use a gas recycle and purge stream. Now, if we change any of these decisions, we will generate a process alternative. For example, purify the hydrogen feed stream, recycle the diphenyl to extinction, purify the hydrogen recycle stream. Now, we will follow the evaluation strategy which goes as follows. Instead of simultaneously evaluating all alternatives, we will first try to get a base case design and next we will evaluate alternatives. So, we will first search depth and then we will search at along the breadth. So, depth first, breadth later, we will adopt. We will first try to guess, we will first try to get a base case design and then evaluate the alternatives. With this, we stop our discussion on lecture 28.